Hello, in this video I'm going to talk about basic atomic structure. So, why do we have to learn about atomic structure and anatomy and physiology, right? Why do we have to learn chemistry at all? I think that Hank can say this a lot better than I can, so let's take a look at what Hank has to say about this.
Hello, I'm Hank Green and I want to teach you chemistry. But please, do not run away screaming. If you give me 5 minutes to try to convince you that chemistry is not torture, but instead the amazing and beautiful science of stuff, and if you give it a chance, it will not only blow your mind, but also give you a deeper understanding of your world. This is just my opinion here, but I think that understanding the world leads to a greater ability to enjoy the world, and there's nothing that helps you understand the world better than chemistry. Chemistry holds the secrets to how life first formed, how cancers are cured, how iPhones have bigger hard drives than 5-year-old laptops, and how life on this planet might just be able to continue thriving, even ours, if we play our cards right. Chemistry is the science of how 3 tiny particles, the proton, the neutron, and the electron, came together in trillions of combinations to form, get this, everything. Now, chemistry is a peculiar science, sometimes talked about as a bridge between the ultra-abstract world of particle physics and the more visible sciences like biology. But calling chemistry a bridge is like calling Eurasia an island. Chemistry has it all. Mad scientists, world-changing revelations, the practical, the impractical, medicine, bombs, food, beauty, destruction, life, and death. Answers to questions you never knew you had. I love chemistry, and I hope I can give you a glimpse into why. So today, let's start out with maybe the biggest idea of all time and move on from there. Stuff is made from atoms.
So that's a short clip from a video called Crash Course Nucleus. Crash Course is available on YouTube. So hopefully Hank convinced you that chemistry is important for pretty much everything, but it's especially important for anatomy and physiology. Chemicals, which are made of atoms, chemicals make up all of our anatomy and all of our physiology. So I want to talk a little bit about atoms. So atoms are the smallest units in chemistry. All matter is composed of atoms. Matter is anything that has mass and occupies space. My laptop has mass and it occupies space. Air actually has mass, not a lot of it, but air has mass and occupies space. So both my laptop and air are matter, and they're both composed of atoms. You're probably familiar with some of the atoms in air, like carbon and oxygen, hydrogen and nitrogen. Understanding the structure of an atom is really critical to understanding how biological molecules like DNA and protein work. So I want to first explore the basic structure of atoms. Atoms are composed of things called subatomic particles. So these are the smaller bits that make up an atom. These include protons, neutrons, and electrons. We will pretend that protons, neutrons, and electrons are the smallest thing in an atom, but in reality, protons and neutrons are actually made of little other particles. But we'll let the nuclear physicists handle that. Protons and neutrons are located in the nucleus of an atom, whereas electrons are located outside the nucleus. So the nucleus is like the center of the atom. That's where the protons and the neutrons are. And then the electrons kind of revolve in an orbit around the outside of the nucleus. The places where we find the electrons are called electron shells or energy levels. So let's take a look at some pictures that go along with this information. So here we see an atomic model for hydrogen and an atomic model for oxygen. So this is what an atom of hydrogen and what an atom of oxygen might look like. We can't actually see these things. We don't even have a microscope that allows us to see these, but based on research, we know what atoms look like. The hydrogen atom is rather simple. It has one neutron in its nucleus, one proton in its nucleus, no neutrons, and it has one electron outside the nucleus. If you notice the black circle here, that black circle is sort of an imaginary line, and it's showing you the pathway that the electron will follow. Electrons are always moving. They're never They never stay in one place for long. And this is a stagnant picture, so we can't really see the electron moving here, but this black line kind of shows you the little orbit that the electron would be following. That black line is representing the energy level or electron shell that I mentioned earlier. So hydrogen's sort of a weird atom because it's the only one that doesn't have any neutrons. If we look over at oxygen, that's more of what we see with a typical atom. We have both neutrons and protons in the nucleus. Here we have 8 protons and 8 neutrons in the nucleus. And then there are 8 electrons found outside the nucleus in those energy levels or shells, if you will. So protons are important in an atom because they determine the type of atom that it is. A hydrogen atom is different than an oxygen atom because they have different numbers of protons. The neutrons are important because they allow for different isotopes for an atom. We'll talk more about those in a bit. And to me, electrons are where all the fun is. Electrons are what enable an atom to interact with other atoms. Electrons are what allow for chemical reactions and bonding, right? And we'll look more into that too. So first, let's talk about the protons. How do we know how many protons are in an atom? Well, let's talk about elements first. You've probably heard of elements. This here is a periodic table of elements, right? So elements include things like hydrogen, oxygen, carbon, and nitrogen, right? An element is a pure substance. It's only made of one particular type of atom, right? So we have an element like hydrogen, right? And then elements like carbon. So let's take a look at hydrogen, right? H is the atomic symbol for hydrogen. So atomic symbols are a letter or 2 letters that represent that particular element. The number above the H, the number in blue, the number 1 here, that's the atomic number. And that's an important number. The atomic number tells you the number of protons in the nucleus of that atom. Right? And if you look, the periodic table is arranged in part according to atomic number, right? And so hydrogen has the atomic number 1, carbon has the atomic number 6. And what makes carbon and hydrogen different is their number of protons. What I'd like you to do right now is to pause the video and answer the questions at the bottom of the screen. We're going to do this quite a few times throughout this video. When you pause the video, answer the questions, put the questions in with your notes that you'll be turning in class. You might have to take a look at a periodic table to answer some of these questions, so you can either like fast forward or rewind the video to the periodic table, or you can open up a separate periodic table in a book or on a web page. So how do we know the number of electrons in an atom? For right now, we are going to assume that atoms are neutral, which means atoms have no charge. This is not true. Some atoms do have charge. They're called ions, and we'll talk about those later. But just so that we have a simple foundation in order to explore atomic structure, we will assume that atoms are neutral. Now, if an atom is neutral, then the number of protons is equal to the number of electrons. And this is because protons have a positive charge and electrons have a negative charge. And if the protons and neutrons are equal in number, then their charges will cancel each other out. Assuming atoms are neutral, what I'd like you to do is pause the video and fill in the blanks at the bottom of the page with the appropriate numbers of protons and electrons. And again, put the answers in with your notes that you're turning in class. So how do we know the number of neutrons in an atom, right? Well, I'm going to tell you how we figure it out, and then I'm going to explain it. The number of neutrons in an atom is equal to something called the atomic mass minus the atomic number. We already know about atomic number. We saw that on the periodic table. And the atomic number is the number of protons in an atom. But what is atomic mass, right? Atomic mass or atomic weight is the average of all the known masses of a particular element. Now, it turns out there can be more than one type of carbon atom. There can be more than one type of sodium atom, right? And what makes them different is their number of neutrons, right? And the atomic mass is an average of all the known masses for a particular element. And we can see the atomic mass on the periodic table too. So let's go back a couple pages to our periodic table. The other number that I didn't explain on here yet is the number in red, and that's the atomic weight or atomic mass. This is called the relative atomic mass because this is, again, the average of all the known versions of a particular element. Right? So for hydrogen, the number of protons is 1, so the atomic number is 1. And for hydrogen, the relative atomic mass is 1.01. So what I'd like you to do right now is to pause the video and using the periodic table, determine the atomic masses for the atoms listed at the bottom of the screen. So the atomic mass for a single atom is the number of protons plus the number of neutrons. So if you were working with just a single atom and you wanted to know what that particular atom's mass was, all you have to do is add up the number of protons and the number of neutrons. And this is because one neutron weighs 1 Dalton and one proton weighs 1 Dalton. A Dalton, by the way, is just a unit of mass, kind of like a gram, but really, 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 really small. So because the weight of a proton is 1 Dalton, and the weight of a neutron is 1 Dalton, all you have to do is add up the numbers of protons and neutrons, and you'll know the weight, the atomic mass, if you will. So that's why we can figure out the number of neutrons based on atomic mass and atomic number. Just take the atomic mass, subtract from it the atomic number, aka number of protons, and that will give you the number of neutrons. So what I'd like you to do right now is to again pause the video and try to fill in the table at the bottom of the screen. I have given you the atomic masses for some particular atoms, and I want you to determine the number of some atomic particles in those particular atoms. And then see if you can answer the question at the bottom of the page. Again, put the answers in your notes. All right, and so what we're going to do here is to pause the video again and answer these questions in our notes too. So hopefully you notice that the number of protons does not always equal the number of neutrons. The most abundant form of sodium on Earth has 11 protons and 12 neutrons. The most abundant form of iodine on Earth has 53 protons and 74 neutrons. So the numbers of protons and neutrons do not have to be equal, and they oftentimes aren't. Isotopes is the word we use to talk about atoms of the same element that have different numbers of neutrons. Right? Because they have the same number of protons, they would be the same type of element. But because they have different numbers of neutrons, right, they will be different isotopes. And because they have different numbers of neutrons and neutrons contribute to the mass, these isotopes will have different atomic masses. So in this picture here, we see the representation of nuclei from 3 different types of carbon atoms, carbon-12, carbon-13, and carbon-14. The electrons are not shown in the electron shells here for simplicity's sake, because right now we're just concerned with protons and neutrons. Carbon-12 is called carbon-12 because the atomic mass is 12, 6 protons plus 6 neutrons. Carbon-13 is called carbon-13 because the atomic mass is 13, 6 protons plus 7 neutrons. And you can see why carbon-14 is called carbon-14. So these are 3 different isotopes of carbon. Right? They're all carbon because they all have 6 protons. They're different isotopes because they have different numbers of neutrons and different atomic masses. When we talk about isotopes, you have to talk about radioactivity because those two can come hand in hand. Some isotopes are stable and some are not. If an isotope is stable, then it's not radioactive, but if an isotope is unstable, then it is radioactive. And to be radioactive, what that means is that it's emitting radiation. Radiation is really just moving energy, and there's different forms of radiation. Right? I have my heater going right next to me right now because I'm in my freezing cold basement, and right now my heater is producing radiation in the form of heat radiation. Right? Not all forms of radiation are necessarily damaging, right? But when radiation comes out of a nucleus, from an unstable nucleus, that often is capable of causing damage to biological systems. That particular type of radiation is called ionizing radiation. And ionizing radiation includes radiation in the form of little particles that break off of the nucleus and fly away from the nucleus. And if you have little particles breaking off of the nucleus, flying away from the nucleus, those little particles could damage things they bump into. Think of this like a old decrepit building that's falling apart, right? It's an unstable building. A little bricks can fly off the building, and those bricks could potentially hit someone that's walking by, right? It's kind of the same idea with a radioactive nucleus. Now, sometimes the radioactive nucleus is emitting particles that can cause damage, but sometimes the radioactive nucleus is just emitting pure energy that can cause damage. Now, when we talk about radiation exposure, we have to consider certain things. Not all forms of radiation exposure are going to be damaging. We have to consider things like how often one is exposed. So for instance, you get a couple X-rays a year maybe, right? Those particular X-rays are not going to cause damage, right? But maybe you've noticed that the X-ray technician will go into another room to press the button to take an X-ray, right? And this is because the radiation technician is taking multiple X-rays in a single day, and the person has to reduce their exposure to the X-rays. Right? So if you had an X-ray taken every single day for 365 days, you would probably get cancer, right? So you have to consider how often you're exposed. You have to consider the dosage too. You know, a very high dose of radiation just once can be damaging. So there are certain things to take into consideration when it comes to radiation exposure and the dangers associated with it. Radiation can be used for lots of wonderful things in medicine, right? What's kind of strange is that cancer can be caused by radiation, but cancer can also be treated by radiation. And we can use radiation for lots of different imaging techniques in medicine. And that's what I want to talk about now, is how we can use radiation in an imaging technique called a PET scan. So a PET scan is sort of an image scan of a body part, and we usually do this to see how well the body part is at using glucose. And if the body part is using glucose well, then it's probably healthy, but if the body part is not using glucose well, then it's probably damaged. So PET stands for positron emission tomography. Positrons are some of those subatomic particles that I mentioned. So I said protons and neutrons are themselves made of smaller pieces, and those include positrons. Emission is just referring to the positron being emitted by a nucleus. And then tomography is using technology and computers basically to get a map of this radiation. So normally what they'll do with a PET scan is they'll take a sugar molecule and make it radioactive. So if you look on the screen here, I have two sugar molecules. And look at the structure. I know we don't know a lot about the structure of this sugar right now, but just look at the pictures and see if you can find the difference between the two. If you notice the radioactive sugar had an F, where the normal sugar had an OH, you're correct. So what we've done here is we have added a radioactive fluorine atom to this sugar, right? And then what we do is we take this radioactive sugar and we inject it into someone's bloodstream. And then we use the tomography to measure the radiation. And so what we're looking at in the bottom of the picture here is a PET scan of the brain. I know that doesn't look a lot like a brain right here, but this is a PET scan of a brain. So a neurologist can look at this picture and tell you what all these different brain parts are, right? So we might do a PET scan of the brain to try to find a damaged part of the brain. So we have built up a library of what a normal PET scan looks like in the brain. So we know which parts of the brain should use a lot of sugar. Those show up red. We know which parts of the brain shouldn't use a lot of sugar. Those show up blue. So remember, if a brain part is working properly, usually it's gonna show up red. So an empty space in the brain, like a ventricle, might be blue. So if we do a PET scan of someone that has like epilepsy, let's say, what we're doing is we're trying to find the damaged part of the brain that's acting as the epileptic center, right? And that's causing the seizures. And sometimes what they'll do is they'll find the epileptic center and do a surgery to remove that in order to stop the epilepsy. But in order to figure out what part of the brain you need to remove, you have to do things like a PET scan, right? So that's what we're looking at in this picture here, is a PET scan from someone who has epilepsy. And the white arrow is pointing to an area of the brain that's likely damaged and acting as the epileptic center. Now, a neurologist can look at this and say, all right, I know that this area here that's blue is supposed to be red. I mean, we don't know that, but the neurologist will know that based on all the normal images that we've seen. And the neurologist will know, okay, this area that's blue, that's showing no glucose usage, it should be showing red. It should be using glucose. So likely that's the area of damage, and it can be acting as the epileptic center. That's it for now. To make sure you bring your notes to class with you next time. Email me with any questions.